Now we consider computation of the second order correction to ground state energy of hydrogen atom placed in an electric field. And the expression for the second order correction is given by equation number 2, and it involves an infinite sum over states phi k other than phi 0. Now it may be difficult to compute this sum, and sometimes one may be able to find alternate methods by which one can compute the first order correction to the wave function psi 01 and thereby compute E02. One such method is provided by Dalgarno and Lewis, and that is what we will discuss now. Now consider this particular term in equation number 2, which is the matrix element of H dash between phi k and phi 0 divided by epsilon minus epsilon k. Suppose if we are able to write that term as the inner product of the state phi k with another state obtained by the action of an operator f on the state phi 0 for all k other than 0. Suppose we are able to do that. Then equation number 2 can be written as, this term will remain there, but this term can be replaced in the following way: phi k f phi 0. Okay. Now this summation involves all states phi k other than phi 0. So it can be rewritten in the following way. You consider summation over all state phi k, and from it subtract the term corresponding to k is equal to 0, and that is what we have obtained here. Now since phi k form an orthonormal set, the vector or the state f acting on phi 0 can be expanded as a linear combination of these states. Now the state f phi 0 is given by a linear combination over states phi k, and the coefficients are given by this expression. Now let's consider the first term in equation 4. So I have rewritten that over here, and consider the term that I have written over here. This is a summation over k, then phi k, then a complex number which is the inner product of phi k with the vector f phi 0. Now h dash is a linear operator, and therefore its action on this vector, this linear combination, is simply sum over k h dash phi k, then this term. Now you take inner product of that vector with phi 0. Now since inner product is also linear in its second argument, this will be equal to inner product of phi 0 with h dash phi k and then this term, and that is exactly what is written on the left hand side, and therefore you can immediately see that the left hand side is equal to this. Okay. Now consider the term within the parenthesis, which is a summation over phi k and this complex number. But what is this complex number? And if you look at equation 5, this is exactly ak. The coefficient of the expansion of f phi 0 in the base is phi k. Okay, so this is ak, and ak phi k summed over k is nothing but f acting on phi 0, as we have seen here. And therefore this term is equal to the inner product of phi 0 with the vector obtained by the action of h dash f on phi 0. Okay, then equation 4, which is this equation, becomes this first term can be replaced by this term, and this term remains as it is, and therefore the second order correction to energy can now be given by this equation. Okay. Now to simplify the matters further, we consider equation 3, which is the defining equation for the operator f, and you multiply this equation with epsilon 0 minus epsilon k, which is epsilon 0 minus epsilon k is guaranteed to be non-zero because k is taken to be different from 0. So if you do that, you get this expression. But this expression is equal to this expression given in equation number 8, which is the inner product of phi k with the vector obtained by the action of the commutator of f with h0 acting on phi 0. And this term is exactly equal to this term. And we will see how that happens in the following step. Consider this inner product. Okay. Now, expanding this commutator, we have the left hand side equal to phi k, then fh0 minus h0 f acting on phi 0. Now consider the first term. h0 acting on phi 0 gives epsilon 0 phi 0, and therefore the first term is epsilon 0 taken outside, then inner product of phi k with f phi 0. So that is the first term that I have written over there. Now considering the second term, you have phi k h0, which is nothing but epsilon k phi k, and the second term becomes epsilon k taken outside, then inner product of phi k with f phi 0. It is again the same number, and therefore this will become epsilon 0 minus epsilon k, and then this term. This is exactly what we have over here, and therefore we can replace this by this term. Okay, and the right hand side remains as it is, and this is true for all k not equal to 0. Now the solution to equation 8 can be written in the following form, that is the commutator of f with h0 acting on phi 0, that is this term over here, can be written as h dash acting on phi 0 plus a constant c times phi 0. To see that this is a solution, consider taking inner product of this expression with phi k, and on the left hand side we have the inner product of phi k with f commutator h0 acting on phi 0, which is the same as this left hand side of equation 8, and on the right hand side you have inner product of phi k with h dash acting on phi 0, that is this term, plus c times inner product of phi k with phi 0. Now k is not equal to 0, and therefore inner product of phi k with phi 0 is 0. And therefore the right hand side of this equation, when we take inner product with phi k, is equal to inner product of phi k with h dash phi 0, which is exactly same as the right hand side of 8 for all k not equal to 0. And therefore this expression is, or this particular form is a solution to an equation given by equation number 8. Now, to find this constant c, we consider the inner product of this equation with phi 0. Okay, then phi 0 inner product with f commutator h0 acting on phi 0 can be expanded in this form. So this is the inner product of phi 0 with f h0 minus h0 f acting on phi 0. But if you consider the first term, h0 acting on phi 0 is epsilon 0 times phi 0, and therefore that term can be written as epsilon 0 times inner product of phi 0 with f phi 0, that is epsilon 0 inner product of phi 0 with f phi 0. Now consider the second term. We have the bra phi 0, then h0 f phi 0. Now bra phi 0 h0 is epsilon 0 bra phi 0, and therefore the second term becomes epsilon 0 inner product of phi 0 with f phi 0. So epsilon 0 and this term, but epsilon 0 minus epsilon 0 is 0, and we have the left hand side equal to 0. Now consider the right hand side. The right hand side of that equation is given by inner product of phi 0 with h dash phi 0, that is the first term, and then c times inner product of phi 0 with phi 0. Since phi 0 is a normal vector, the inner product of phi 0 with phi 0 is 1, and therefore you have this left hand side equal to 0, and this is equal to inner product of phi 0 h dash phi 0 plus c, and c can be given by equation number 10. Now we substitute this value of c in equation number 9, okay, and therefore the equation for f becomes f h0 commutator with phi 0 gives h dash phi 0 minus, you replace c by this value, that is what you have over here, multiplying phi 0. Okay, now this left hand side of equation 11 can be simplified by considering this equation. Commutator of f with h0 is f h0 minus h0f. When it acts on phi 0, the first term gives h0 acting on phi 0 is epsilon 0 phi 0, and therefore this is epsilon 0 f phi 0. Then the second term remains as it is, and therefore you can write this term as epsilon 0 minus h0 acting on f phi 0. So use this in equation number 11, you will end up with equation number 12. Okay. Now this equation has a property that the addition of a multiple of phi 0 to f phi 0 will not alter the left hand side of the equation. So that means the solution to this equation has a freedom that to any solution we can add a multiple of phi 0 and equation 12 remains unaffected. That means the new function obtained by the addition of a multiple of phi 0 to f phi 0 is also a solution. Okay, so now this freedom can be used to choose f phi 0 to be orthogonal to phi 0, as we have seen in our analysis of perturbation theory earlier. Now since we can choose f phi 0 to be orthogonal to phi 0, equation 7, that is this equation, gets simplified, because this term over here is exactly the inner product of phi 0 with f phi 0, which we have chosen to be f phi 0 to be orthogonal to phi 0, and therefore this will become 0. So the equation for the second order correction to energy becomes simpler, and it's given by the first term only. So we have the second order correction given by this equation if we choose this particular choice. Okay. Now equation number 12 is exactly same as the first order correction term in perturbation theory. If we identify f phi 0 as a first order correction to wave function and this term over here as a first order correction to energy, and therefore we identify f phi 0 as the first order correction to the eigenfunction. Okay. Now to summarize the Dalgarno and Lewis method, we have two equations. The first gives us f, and that equation is this one, this equation, which says that the commutator of f with h0 acting on phi 0 gives h dash phi 0 minus, then the expectation of h dash in the state phi 0 multiplying phi 0. That is the first equation, and that determines the operator f. And the second equation gives the second order correction to energy, and it is given as the expectation of the operator h dash f in the state phi 0. And for this equation we have chosen f phi 0 to be orthogonal to phi 0. That is how we could set this to be 0, so that the expression for E02, that is a second order energy correction, becomes this particular term over here. Now we apply the method of Dalgarno and Lewis to hydrogen atom in an electric field. Now consider the hydrogen atom in the electric field problem. The unperturbed Hamiltonian H0, which is the same as a hydrogen atom Hamiltonian, is given by P square by 2 mu plus Vr, where mu is the reduced mass and P is the momentum, V is that potential, hydrogen atom potential, and the perturbative term due to the presence of the electric field is given by H dash equals the electric charge times the magnitude of the electric field, then R cos theta. The ground state eigenfunction of H0 is given by e to the power minus r by a0 multiplied by this normalization factor, where a0 is the pore radius and r is the radial distance, the radial coordinate of the hydrogen atom electron. Now to solve the Dalgarno and Lewis problem, where we first have to find the operator f using this equation, and we have all the ingredients to be used here. H dash is known, phi 0 is known, and f is the only unknown in this equation. And to simplify the matters, we first assume that f is a function of the position operator only, and in the position representation this will be a function of the position vector. Then we need to compute this term, the commutator of f with H0. We know that f is a function of r only, and the functional form, the form of H0 is also known, and therefore we can compute the commutator of f with H0. So substituting for H0, we have the commutator equal to f, which is a function only of r, then p square by 2 mu plus v of r. So since f is a function only of r, it commutes with this potential term over there, and this is simply equal to, since 1 by 2 mu is also a constant, it can be taken outside, and therefore this commutator becomes 1 by 2 mu times fr commutator with p square. Now p square has this form minus h bar square, then Laplacian, and minus h bar square can be taken outside, so we get minus h bar square by 2 mu, then the commutator of fr with del square. To find this commutator, we consider its action on an arbitrary function of r. So fr commutator with del square acting on c of r can be written in this form, because first fr will act on del square c, then minus del square will act on the product fr and cr. Expanding this, we will finally get this expression. Consider this as some operator acting on the function c of r, and the first term can be written in the following way. This is equal to minus del square f multiplying c of r. So that is what we have here as the first term, and the second term is 2 times gradient of f of r, then inner product with the dot product with the gradient of c of r, and which can be written in this form: 2 times gradient of f of r dot the gradient of c of r. Okay, so this can be written in a compact form like this. So minus del square f plus 2 times gradient of f dot del acting on c of r. Okay, since c of r is an arbitrary function of r, we can write the operator equality. The commutator of f of r with del square is equal to the expression given in the square brackets multiplied by minus 1. Okay. Then f commutator with h0 will become this term, because in f commutator with h0 we have an additional factor minus h bar square by 2 mu multiplying the commutator of fr with del square. So you multiply this with minus h bar square by 2 mu and you will end up with this equation. Okay. Then in the Dalgarno-Lewis equation, we have on the right hand side this particular term. This is in fact the first order correction to energy starting from the state phi 0, and we have already seen that this term is 0. and therefore on the right hand side you only have this term. Okay, then our equation becomes fh0, so fh0 acting on phi 0 is equal to h dash phi 0. So fh0 is given by this equation, and that should act on phi 0. Phi 0 is given by this expression, and that is equal to h dash acting on phi 0. Okay, so on both terms, on terms on the left hand side and on the right hand side, you have this constant factor 1 by pi a0 cube to the power 3 by 2, which can be cancelled, and you will end up with this equation number 14. Okay, so f commutator with h0 is this, and this will act on e to the power minus r by a0, and on the right hand side you have h dash, which is given by er cos theta, then phi 0 of r, and you have this exponential minus r by a0 times that particular constant, which can be cancelled with the same constant on the left hand side, and you will end up with equation 14. Now we see that this is a function only of the radial coordinate. Now we have to compute its gradient. So the gradient is in general given by this expression in spherical polar coordinates, and since this is a function only of the radial coordinate r, the derivatives with respect to theta and phi become 0, and you will end up with the action of this term on e to the power minus r by a0, which is equal to this, which is in fact along the radial direction. Okay, now we have to take inner product of that result, that is the gradient of e to the power minus r by a0 with the gradient of f of r. So gradient of f of r dot del e to the power minus r by a0, but the second vector is along the radial direction. So if you take inner product with this, we only have the component of this along the radial direction remaining, because all other inner products along all other directions, that is the theta direction and phi direction, when you take inner product with this, will become 0. Okay, so you have the r component of this del e to the power minus r by a0, which is given by this dot gradient of f of r, which is equal to this term, which is written as it is, times the radial component of this thing, which is equal to derivative with respect to r of f. So we have the simplified expression for this particular term. Okay, substituting this over here, equation number 14 becomes del square f remains as it is, and this term can be taken to the right side. So you have del square f minus, now for this you have 2 by a0 minus 2 by a0 times e to the power minus r by a0 into df by dr. So that can be, so df by dr and minus 2 by a0, then this factor is there, but the same factor appears on the right hand side also, and therefore it can be cancelled out. Then this h bar square by 2 mu can be taken to the right side, and it becomes 2 mu by h square. Then these factors are there, this r is there, cos theta is there, and this factor is also there, and that can be taken together to define a new constant k, which is 2 mu e capital E divided by h bar square. Then the right hand side of the equation becomes k r cos theta. Okay, now so this is an expression written now in spherical polar coordinates, so we have to express this del square also in terms of the spherical polar coordinates, but we immediately see that we can separate this in the radial and the angular coordinates, and since this del square Laplacian is separable in spherical polar coordinates, and we have the spherical harmonics as a complete set of functions to expand in the angular coordinates. We can write our function f of r as a linear combination of the spherical harmonics with the coefficients depending upon the radial coordinate r. Okay, so I have written f of r as a linear combination of all spherical harmonics. Now on the right hand side you have cos theta, but you also know that this is equal to square root of 4 pi by 3 times the spherical harmonic 1 0. Okay, now we also expand the Laplacian in terms of the spherical polar coordinates, and then substitute for fr using this expansion. Then we see that this equation becomes this expression. Okay, now the first term involves derivative with respect to r only, and in this expression the only term that depends upon r is the small f, and therefore ylm remains unaffected, and therefore we can write the first term as this, which involves derivative only with respect to derivative of f with respect to r, and in the second term you have derivative with respect to theta, and in the third term you have derivative with respect to phi, and therefore you can separate out this f factor from those derivatives because it depends only on r. So f has been taken outside, then that factor of r square. Then in the second term you have derivative of the spherical harmonics with respect to theta, and in the third term you have derivative of spherical harmonics with phi, and they can be grouped into this particular form. But we have already seen while discussing the hydrogen atom problem that the action of this factor, that is 1 by sin theta d by d theta sin theta d by d theta plus 1 by sin square theta d square by d phi square, acting on the spherical harmonics, is given by this particular value, that is minus L into L plus 1 and ylm, and therefore we can substitute by this equation and we will end up with equation number 16. So you have ylm here, and the action of this is like minus L into L plus 1 times ylm, and you have this factor also, this fourth factor involves derivative with respect to r only, and therefore it affects only on this. So ylm comes out as a common factor, and therefore we can write this expression as equation number 16, where I have taken ylm outside this square brackets, and all the terms within the square brackets depends only on the radial coordinate r. And on the right hand side you have this cos theta factor, which is in fact proportional to y10, and I can write that as square root of 4 pi by 3 kr times y10. Now since ylm is an orthonormal set, the coefficients of ylm on the left hand side of an equation should be equal to the corresponding coefficients on the right hand side. And therefore equating the coefficients of ylm on the left hand side and the right hand side of equation 16, we have the following equation. So whatever is on the square bracket is a coefficient of ylm, and that will be equal to 0 whenever lm is not equal to 10. When lm is equal to 10, the coefficient is given by this. So we have this expression. So these square brackets, okay, and that is equal to square root of 4 pi by 3 times kr if L is equal to 1 and m is equal to 0 and is 0 otherwise. Okay, so all FLM other than F10 satisfy the homogeneous equation, and only F10 satisfy the inhomogeneous equation. Okay, so in general the solution can be written as the sum of the homogeneous part plus the non-homogeneous part, and now we check the asymptotic behavior of the homogeneous equation to see if it can be accepted as a solution that will give rise to a normalizable wave function. Now if d is not equal to 0, we see that f phi 0 goes like e to the power r by a0. That's because of this. Phi 0 goes like e to the power minus r by a0, and when you multiply phi 0 by f of r, the second term will become d times e to the power r by a0, and this term becomes infinity as r tend to infinity, and therefore the expectation given by this expression, which is in fact the second order correction to energy, will become infinity. And not only that, f phi 0 is proportional to the first order correction to the eigenvector, and this will lead to a non-normalizable correction to the ground state wave function, and therefore we cannot accept this as a solution, and that lead to a normalizable wave function, and therefore we have to choose d is equal to 0. So the only remaining part in the solution is this constant c, and if we choose f is equal to c, then we will run into problem if we consider the r tend to 0 limit. To see that, consider equation 17, and in this case, as r tend to 0, L into L plus 1 by r square times f of r becomes infinity unless L is equal to 0. If L is equal to 0, this numerator itself will be 0, and therefore this will not be affected. However, when L is not equal to 0, then this term diverges at r is equal to 0, and therefore we cannot have this solution f is equal to a constant for any L other than L is equal to 0. Okay, so our acceptable solution is if Lm is equal to a constant only for L is equal to 0. But then if L is equal to 0, M can only have one possible value, that is also 0, and therefore F00 can be taken to be a constant and all other FLM has to be 0. Now, what will be the solution when we take F00 to be a constant and all other FLM to be 0? So we have seen here that F will be the product of FLM and YLM and summed over all LM. So if we take F00 to be non-zero and all other FLM to be 0, then this equation becomes F00 times Y00. Okay, so now F00 is a constant and therefore F of R will be proportional to Y10. So that means F homogeneous would be, since Y00 is a constant, this would mean that F homogeneous is another constant. Now what will be F50? F50 would then be equal to that constant multiplying phi 0. But we have already stated that we will be choosing an F50 which is orthogonal to phi 0. And therefore we cannot choose F50 to be C dash phi 0 with a non-zero value for C dash. And therefore we should set C dash is equal to 0. So finally, we have seen that the solution to the homogeneous part cannot be an acceptable solution of F. Okay, so now we concentrate on the non-homogeneous part, which has a non-zero solution only for L equal to 1 and M equal to 0. Okay, so that equation is given by equation 18, and this equation, second order differential equation, and it has a regular singular point at r is equal to 0, and therefore we can construct a power series solution with a leading term given by r to the power s with s greater than 0. And the value of s will be determined by the corresponding initial equation, and it can be worked out, and the power series method immediately gives the solution given by this expression. So F10 is equal to this prefactor multiplying R plus R square by 2A0. Okay, so now that we have got the solution for F, and that is non-zero only for L is equal to 1 and M is equal to 0, and the general solution for F can now be written as F10 times Y10, but Y10 we already know is proportional to cos theta, so we can write our expression substituting for Y10 over here. We can write the solution in this particular form. Now that we have got f of r and h dash r, we can use equation 13b, that is the equation that gives a second order correction to energy, to compute the second order correction. So this is given by this expression. The second order correction to energy is given by this expression. Now we know the functional form of phi 0, we know what h dash is, and we have just computed f of r, and we know phi 0. So in the spherical polar coordinates, this will become the following integral. So substitute for phi 0, h dash f, and then the volume integral is given by integral from 0 to 2 pi of d phi, and integral from 0 to pi of d theta sine theta, and integral 0 to infinity over dr r square. Okay, now putting all factors together, and collecting all the phi terms, theta terms and r terms together into these three parts, we can write the integral in the following form. Now d phi integral has no other term with phi dependence, and therefore it simply evaluates to 2 pi, and the theta integral is simply this, which is equal to 2 by 3, and the integral over r will now have this form, where an r square comes from the integration measure in spherical polar coordinates, and there will be this term r plus r square by 2a0, and multiply that with r square, from the integration measure, and an r from h dash. You will have r to the power 4 here and r to the power 5 by 2a0. Then from this expression for phi 0, which goes like e to the power minus r by a0, and since we have two phi zeros, we will have e to the power minus 2r by a0, and all other factors have been collected and put into this prefactor. So the r integral is this, and this can be evaluated using converting this into a gamma function type integral, and this can be evaluated to get this value 27a0 to the power 5 by 16, and putting them together we will get this expression, and the second order correction to energy is proportional to E square, and it is negative, as we have already seen while discussing the second order correction to the ground state energies, because now the second order correction to ground state energy should be negative, and we have got a negative value over here. Now we want to interpret this result. We have already seen that the expectation value of the polarization operator is 0 in the ground state of the hydrogen atom, and therefore we conclude that there is no permanent dipole moment when the hydrogen atom is in its ground state. Suppose you have a linear isotropic material and you place it in an electric field, and an electric dipole moment will be induced in it, and it will be proportional to the external electric field, and so the induced dipole moment is given by this expression, where mu is equal to alpha times E, and this alpha is called the polarizability of the system. Now if we change the electric field by a small amount dE, the change in potential energy of the system is simply given by minus dE dot mu E. and thus the change in energy as we slowly increase the field and the system develops a dipole moment and reaches a final value as the field changes to a value E is given by the following expression. This is equal to integral of du with E going from 0 to E. So you substitute the expression for du here, and which we have over here. The expression for du is given over here. You substitute that over here. Then mu E is replaced by this expression, and alpha can be taken outside, and therefore this is equal to integral from 0 to E, then dE dash dot E dash. But this expression is half of the derivative of the dot product of E dash with itself. Okay, so this is a perfect differential, and therefore the integral is given by the value of this function evaluated at the limits. Okay, so this is minus half alpha E square evaluated at E minus the same expression evaluated at 0, because at 0 this will be 0, and therefore this integral evaluates to minus half alpha E square. So if you have a linear isotropic material in an electric field, a dipole moment will be induced, and as a result it will undergo a change in energy equal to minus half alpha E square, where alpha is called the polarizability of the system. Now we compare this expression with the second order correction to the ground state energy of the hydrogen atom when placed in an electric field. This is also proportional to E square, and therefore we identify this change in energy with the change in energy that is reflected in the second order correction. So if we equate those two terms, we can compute alpha, and we see that alpha is given by 9 A0 cubed by 2k.